Dear students, in this lecture we see about the physical vapor deposition of forming a thin film. The physical vapor deposition involves the conversion of solid material into a gaseous phase. As I told earlier lecture, here the physical vapor deposition is purely a physical process. There is no chemical reaction involved. So the starting material will be the same material we should take, which has to be formed as a thin film. For example, if you want to make a thin film of silicon wafer, then the starting material what we take should be silicon. And like that we take the same material which is converted to gaseous phase, and then it is settled over a deposit over a substrate. So the PVD conversion process includes thermal evaporation, and this thermal evaporation is done using either resistive heating, electron beam heating, or it can be done through laser ablation. The laser ablation either or pulsed laser deposition or spark erosion and sputtering. These are some of the process which can be done in order to convert to the vapor state. The most of the thermal evaporation techniques required a high vacuum. Generally, the vacuum should be maintained of the order of 10 power minus 5 torr, and the boat is fixed between the electrodes, which is kept at the bottom. For example, you can see the diagram here. In this diagram, so this is the boat which is fixed between the heater in order to heat it, and the substract is, or the substract holder is placed at a distance of 30 to 40 centimeter from the boat. So this is the boat here, and this is the substract. The substract is here and the boat is here, and the distance between these two, this boat and substract, this distance is nearly about 30 to 40 centimeter, and it is deposited on the substract. And then place the bill jar on these and create the vacuum up to 10 power minus 5 to 10 power minus 6 torr. And the vacuum is, after achieving the vacuum, switch on the power supply in the electrodes so that it is get heated, converted to vapor, and the vapor is deposited over the substrate. So this is the general setup. So this is a bill jar. It consists of a bill jar, and it is highly evacuated chamber, and the board is present at the bottom, which consists of the material which has to be formed as a thin film, and it is kept between the electrodes where it is going to get heated. Once it get heated, it will convert it to gaseous phase like this, and these atoms will settle down on the substrate. When it settle down on the substrate, it will settle down as atom by atom and then layer by layer. First it will settle down as atom by atom before it forming a first layer, and the second layer of atom will form above the first layer of atom as atom by atom, layer by layer. In this process it is grown, and if we have a definite thickness, we can peel it off to get the thin film. And above this, a heating arrangement is provided, so which is called as a parabolic heater. And what is the use of this parabolic heater is, suppose if you don't have a uniform thickness, so thin film, we know that it should possess uniform thickness. If the uniform thickness is not maintained properly, we can use this parabolic heater, and we can get it to a uniformity. The uniform thickness can be achieved by using the parabolic heater. And here there are two different diagrams are given. So in this, there is no laser ablation is not used, and only the filament winding is used to heat it, or the electrode heating is done. In certain materials, we cannot use only the filament winding or the electrodes. We need the use of a laser. High power laser is used to ionize the material, or we can convert the gaseous phase is obtained. The gaseous phase of the atoms is obtained using some high power laser. We create that gaseous phase, and then the formation of thin film occurs. Next, we see the chemical vapor deposition. As the name indicates, here a chemical reaction will occur, and generally the uh, starting material will be in the gaseous phase, and that will undergo some thermal decomposition in order to occur a chemical reaction on the substrate. Over the substrate, the chemical reaction will occur, and through that, the thin film is synthesized. So, the basic principle involved in this technique is decomposition or partial dissociation of the wafer phase species, and the subsequent deposition on substrate gives thin film. So, this is the basic principle. And depending on the thin film to be grown, the respective substance in the form of chloride should be taken. For example, to form silicon dioxide, then we take the silicon chloride as the starting material. And to form the tin dioxide, we take tin chloride as the starting material. So the starting material will be taken in the chloride form, and apart from that, we take a few other gaseous atom which can involve in a chemical reaction to form silicon dioxide or tin oxide, as the equation follows. To form silicon dioxide, this is the equation to be followed, and to form tin dioxide, the equation is as follows. And here in this diagram you can see here, so the starting material is taken in the form of gaseous state, and this gaseous atom is allowed to get into the chamber where the substrate is placed at the bottom, and it is heated to a high temperature. And as it is heated, this to a high temperature, the chemical reaction will be initiated on the substrate, and the pressure is maintained such that the chemical reaction is occur only on the substrate, and it should not occur in the air medium. If it occurs in the air medium, then it will fall on the substrate as a dust particle, which will affect the thickness of the thin film. And the remaining gaseous particles which doesn't get involved in any chemical reaction is sent through this outlet. And what is the necessity for this chemical vapor deposition over the physical vapor deposition? The main reason is, you can see here in this substrate, so in between this small substrate there is certain gaps. The side walls cannot be coated uniformly in the case of a PVD technique. If the substrate is in this form, we cannot coat properly on the side walls. Only on the top walls it can be coated efficiently, not on the side walls in the case of a PVD method. But here on the side walls it will be coated uniformly. The top substrate, the top layer of the substrate will have uniform thickness. Even the side wall will have a uniform thickness, and in that we call that as an aspect ratio. Okay, ratio of diameter to the depth is called as aspect ratio. So the CVD technique has a very good aspect ratio when compared to PVD technique, so that even the side walls can be coated uniformly. So that is the advantage of this PVD. Let me say advantage of CVD over the PVD technique. So what is the disadvantage of the CVD technique? So many of the gases used in the CVD are highly corrosive and toxic. So hence good safety measures has to be taken. So it is highly corrosive and highly toxic nature. The cost of the high purity chemical is also high. The cost value is very high, since the cost of the high purity chemical is very high. The temperature and the pressure has to be controlled well. As I told, if it is not controlled well, then what happened is that it will form as a dust particle on the wafer. It will fall on the wafer as a dust particle. That will lead to certain drawbacks. So the first, the major drawback is given at this point, indicates what is the drawback. The temperature of that such formed the temperature cannot be raised arbitrarily during the chip manufacturing, because the transistor is made with impurities doped in particular location. When the wafer is heated, the dopants will move and the transistor will not function properly. So if it acts as a dust particle, then it will affect the chip function, and the transistor will not work properly. So the temperature and pressure has to be controlled well in order to get a uniform thickness, in order to in order to get the reaction occur only on the top of the substrate rather than in the air medium. So with this I stop. The next two techniques we see in next lecture.